Okay, welcome to class, everybody. So, in the light of our difficulty in using the platform, so I'm going to decide to make this video. So, I quickly want to go through the homework. Now, one thing I realized about the homework is the fact that we did not make room for extension in our table. We just use the scale reading as it is as our extension, which actually is not proper. And I also felt maybe in a way I also misled us to add the weight to the added load. Because if you take a critical look at it, the added load are the ones that are responsible for the extension. What does that mean? It means that when you had, if you did not add any load, the scale reading is at 4.02 cm. And of course, it also means that there is no extension here. But if you had a load of 10 Newton, it will cause the string or the spring to extend from 4.02 to 4.12. So the extension here will be 4.12 minus 4.02. Likewise, if you have an added load of 20 Newton, it will cause an extension of 4.2 to 4.22 from 4.02. So it means the extension here will be 4.22 minus 4.02. So in essence, you have to subtract 4.02 from all the scale reading to determine the extension. And you need not add any weight to this added load, because these are the actual loads that are causing the extension. So if that is clear, I think we can then proceed with this understanding. Now the code. Okay, just like we all know how to do the code, the only thing, though, you will see that you did not see any cell here for the upload to the Google Colab, because I did this on Jupyter. It's another platform for running Python notebooks. So here, what I've done here is that to determine the extension, I use the scale reading and subtract 4.02 from all the scale reading. This is a centimeter. I have to divide by 100 to convert it to meter. So that's what I've done, and that's why you have this table here of force against extension. So you have 0, 10, 20, 30 to 60, and you have 0, 0.001, 0.002 to 0.006 as the extension. So of course the next thing to do is to plot the graph. Now if you do a plot of the graph, then from the graph you can see it's a straight line, which is evident from Hooke's law. So definitely Hooke's law is obeyed throughout this whole journey. The next thing of course is to determine the slope. So of course try to use a very big triangle. So I'm using this triangle 60 to 10 here. So 60 Newton to 10 Newton, 0.01 to 0.06. So to calculate that gives me slope of 10,000 Newton per meter. So that's of course the spring constant based on Hooke's law. So with that in mind, so I think for this part, despite even the not using the extension as you're supposed to derive it, I marked this for all of us majorly. I think generally I gave generally 878, because I told you guys that I want us to be able to do some research about Python and do some other things to the codes, probably graph, do some other things to make the graph look better, but most of us did not go in that direction. So that's why I'm giving you guys 8 out of 10. So the next thing is to now look at problems A and B, where I've realized most of us didn't really understand the question. So let's go back to the question. A, we have to, after graphing the values, we have to find the length of the wire. So what are you supposed to do? What you're supposed to do is to derive a relation from Young modulus. So from Young modulus, we know that Young modulus equals to stress over strain, and that will be force over area, which is stress, divided by extension over length. If you put that together, Young modulus will be force times length divided by area times extension, which will give us this. We cross multiply this, we are left with FL equals to YAE. If you divide by L, and the reason why we are doing that is that we want a relation that will be close to F equals to K. You can see they are now similar. We want to do that because we want to use the slope, information of the slope, to make further deductions. Evidently, K is, which is the slope, is equals to YA over L. So this is all you need to do. Now you know Y, you're given Y already, and you can calculate A from the diameter. Then L will be easy to derive. So what do we do? From this relation itself, L will be equals to YA over K. Y is 1.8 times 10 by 11 Pascal. D is 0.7 millimeter, and which is equal to 7 times 10 to the minus 4 meters. If you compute the area, you will get 3.85 times 10 to the minus 7 meters square. Now compute the length. 1.88 times 10 to the minus 11 times 3.85 times 10 to the power. Oh, sorry, this should be minus 7. So minus 7 here with the 4 here. That would make it like a minus 11 together. So at the end of the day, you have your length to be equal to 6.93 meters. So this is a mistake. It's raised by minus 7. So that's just it. You get it at 6.93 meters. Now the B part, we have to find if the proportional limit occurred at 4.50 centimeter. What is the stress at this point? So what is this question telling us? Now what this question is telling us is that proportional limit at this, we want to determine the stress at that point. So what you need to do, of course, is to find the extension first at that point. And what have we done to do that is to subtract 4.02 centimeter, which is the point after which the spring is stopped. So if you do that, 4.50 cm minus 4.02 cm, you will get 0.48 cm, which to meter will be 0.0048 meters. There are two ways. Now we have to determine the force. There are two ways to determine the force. You can trace the graph. You can trace 0.0048, trace it up, and determine the corresponding value of the force from the graph. Or alternatively, since you know the value of K and this extension, you can determine the force, because force will be equals to K, which is 10 to the power 4, which is 10,000 Newton per meter, multiplied by the extension that you have just calculated, 0.0048 meters. That will give you 48 Newton. So that's the force. The force that will produce an extension of 0.0048 meters. Knowing the force, and you know the area, of course, you can now determine the stress. So that will be 48 Newton divided by the area, which is 3.85 times 10 to the minus 7 meters squared. That will give us 1.25 times 10 to the power 8 Pascal, which is what you are required to do. So, but most of you didn't really get this A and B part. So, but now you have the correction. You know how to go about this if this comes out in either test or exam. Now let's go to more interesting problems. So I've put up some standard problems for us that I want us to look at. So I've put up these problems for us. They are standard problems for us to look at. So now, in my opinion, we're now moving ahead to look at more standard problems that away from the small problems you have treated, which are more like high school standard. So let's now go to the university standard question. Now, question 1. We're told that a 1.05 meter long rod of negligible weight is supported at its end by these two wires, A and B. And we're told that the wires are of equal length, but the diameter of B is twice that of A. Now, given that the Young modulus also is of A is 1.5 times that of B, we have to compute the value of this x. This x here is from the point at which the weight here attached to the rod to the end of where the wire A meets the rod. We should find x that will produce equal stress in A and B and equal elongation in A and B. Now this is an interesting problem. And this kind of problem, you can see, from what you can see, this looks like some of the things you do in moments of forces. So this kind of linking moments of forces with elasticity. And it's an interesting problem. I love this problem. In your homework, it's also there. So this is an interesting problem. So how do you approach this problem? Just pay attention and you understand how I go about it. Now, because of the urgency and other things, I could not type this out, but I hope my writing will be clear enough for us. So I've just redrawn the diagram here. So I said let the tension in the wires A and B, because of wires, they are connected to the rod, so there will be some kind of forces in the wire which are called tension. Tension in wire A is TA and tension in wire B is TB. So if we decide to take a moment about point P where the weights meet the rod, take moment about that point to be 0, so that then on using the principle of moment, that sum of clockwise moment equals to sum of anticlockwise moment as the way it is. So definitely you have it like the TA here multiplied by x will be equals to, if this is x, definitely this other length will be 1.05 minus x. So it will be TB multiplied by 1.05 minus x. I want to believe that we have not forgotten our moments completely. So we can call this equation 1. Now, the question is asking us to compute x for equal stress in A and B. So we'll take it from there. Equal stress in A and B means stress in A equals to stress in B. And what is stress? Force over area. Only that in this case, the forces are the tension from the rope or the wire. Sorry. So TA over area of A equals to TB over area of B. You can put that as equation 2. Now let's now compute the area. Area equals to pi d square over 4. So which means that area of A will be pi d diameter of A square over 4, and that of B will be pi diameter of B square over 4. So but we are told that diameter of B is twice that of A. So you have a case where now using this now we can, instead of writing diameter of B, we now write 2 times diameter of A. And if we evaluate this, 2 square is 4. This 4 will be outside, and you have dA to be squared. So, and this is similar to, we now have here pi d A squared over 4, which is similar to area of A. So I can rewrite this as AB equals to 4 area of A. So doing that now, from equal stress in A equals to equal stress in A equals to stress in B, I'll instead of writing area of B, I'll write 4 times area of A. So with that, the area of A can cancel out. Then I'll be left with CA equals to TB over 4. So that means TB equals to 4 CA. I will now put this in the first equation, which is the moment equation they will derive from the principle of moment. I'll substitute for T of B here in terms of T of A, then I will be able to solve for X directly. Let's see how that plays out. If I substitute for 3 in 1, so instead of writing T of B, I decide to write 4 T of A based on what we derived. So TA will cancel out T8. We'll be left with X equals to 4 times 1.05 minus X. If we expand that, we have 4.2 minus 4x. So collect like terms, x plus 4x equals to 4.2, 5x equals to 4.2, and x equals to 4.2 divided by 5 to give us 0.84. So I believe that's clear enough. Now let's look at the B part. For equal elongation in A and B. Elongation means extension. So the only way we'll compute our extension from easily is from our strain. Remember, strain equals to extension over length. So what do we do? From Young's modulus equals to stress over strain, that equals to tension, in this case which is our force, over area divided by extension over length. Putting that together, we have Young's modulus equals to CL over AE. So our extension now will be, if you multiply and divide, you have tension equals to tension times length divided by A times Y. So the same way we did equal stress in A and B, we will do equal extension in A and B using this relation. So now is to do all the substitution. We are told that they are of equal length, so LA equals to LB. We are told that y of A equals to 1.5 y of B, and we calculated or deduced area of B equals to times area of A. So let's put all these three inside this equation. If we do that, instead of writing y of A, I'll write 1.5 y of B. Instead of writing L of B, I'll write L of A because they are equal. Instead of writing A of B, I'll write 4 area of A. If I do that, you realize that LA can cancel out LA, YB can cancel out YB, and AA can cancel out AA. And what I'll have left will just be TA over 1.5 equals to TB over 4, which will imply that TB equals to 4T over 1.5, and that will be 8TA over 3. Now, I'll not also take this equation again to the first equation derived from the principle of moment, this equation. So only that instead of writing TB, I'll write 8TA over 3. So what do we do now? TA will cancel out TA. Multiply 3 to the other side, you have 3x equals to 8, 1.05 minus x. Putting that together, 3x equals to 8 times 1.05 is 8.4 minus 8x. Now collect like terms. 11x equals to 8.4, x is 8.4 divided by 11, which is 0.76 meters. So that is that about that question. Yeah, in our homework, I gave all of us a similar problem to solve. So we'll talk about the homework after this two soft problems I'm looking at. Now the second question, let's go to the second question. Question 2 is asking us to, we are told that a steel cable with cross-sectional area 2.50 centimeters squared supports a 5200 Newton elevator. The elastic limit of the cable, which is the wire, is 3.0 times 10 per 8 Pascal. If the elevator is moving at constant velocity, how many men of 100 kg each can the elevator carry so that the stress does not exceed 20% of the elastic limit? It's a very simple problem. And it's a standard problem, just like away from the high school standard elasticity question. This question links the problems, some of the problems you might have looked at in your first semester is 101, which has to do with elevators. So it links the elevator problems to the elevator problem, it links it to elasticity. So what do we do? How do we solve this question? So what we do, let's go to, okay, what we do, because this is the steel cable that is supporting this elevator, and the question is asking us that, let's say there are men, this lift or elevator is to carry men of 100 kg each. The question is, how many men will this elevator be able to carry? What do we do? We understand from the second law of motion, that summation F equals to ma. But meanwhile, we are told that this lift elevator is moving at constant velocity. That implies that acceleration is 0. And if A is 0, it means that ma also equals 0. So what do we do? Now if ma equals to 0, it means summation F equals to 0. But there are only two forces here, which is the tension and the weight of the elevator. If we put that together, T minus W, because T is facing upward direction, which is positive, W is facing downward direction, which is negative. So we have T minus W equals to 0, which implies that T equals to W. You can believe that as equation 1. Now in the same vein, now there are two sets of weights involved in this W. The weight of the elevator, which is already given to be 5,200 Newton, and the weight of the men in that elevator. But let's proceed to see how to calculate the tension. The tension in the wire can be deduced from the stress. Stress equals the tension over the area of the cable. But mind you, we are told that 20% of the stress. Let me quickly go back to the question. The question says, so that the stress does not exceed 20% of the elastic limit. So we are computing for 20% of this stress. So what do we do? 20% of the stress, we are already given the stress is 3 times 10 raised per 8. So 20% of the stress equals the tension over area. So the tension will be 20% of the stress multiplied by area. So that will be tension equals to 0.2, which is 20%, times the stress, 3 times 10 raised per 8, times the area, 2.5 cm square, will become 2.5 times 10 raised by minus 4 meters square. If we put that together, we will get 15,000 Newton as the tension in tension in the steel cable. Now going back to this formula, T equals to W. So T equals to W of the elevator plus W of the men. So that will be 15,000 equals to 5,200 plus WM. WM, then subtract 5,200 from 15,000, that will give us 9,800. Knowing that W equals to mg, you can compute the mass as W over G, which is 9,800 divided by 9.8. That will give us 1,000 kg. This is the weight, this is the mass of all the men in that elevator. Now, if each of them are to be 100 kg, how do we determine the number of men? It's just to divide the 1,000 divided by the 100, and that will give us just 10 men. So that's just the two problems. I believe that solving these two problems will help your understanding of the homework you are given. So let me quickly just go through the homework also. There are 6 interesting problems here. There are 6 interesting problems I put together. By the way, the deadline is on Thursday. So on Thursday, the deadline 6 p.m. in the evening. So you can see question 1 is also this kind of problem I've solved earlier. Question 2 is different. Question 3 is the same kind of problem, but just with some modification. Question 4 is a different type of problem. Question 5 similar, and question 6 different type of problem. So since we are in group A to F, I only want us to answer 2 questions. That means each of us. So all of us in group A, we have to do this question individually, not group work. Question 1 and 2. In this arrangement, we should answer this question. So I believe that based on the explanation of the ones I've done earlier, it will help you in solving this problem. So I think that should settle it. Now lastly, I want us to consider packages to present that will help us to present our solution in very clear and presentable format, rather than just writing and snapping it and attaching to my mail. I want us to be able to type like this and present it like this, our calculations, so that way it's easy. So there is a software I will introduce to us. It's called MathType. I will introduce it to us, and I'll probably send us there's a trial version for 30 days that you can all install on your laptop, and you can use. I'll look for videos that will show you how to use the MathType, so that you can use it. You can copy from the MathType into Word document, so that you know how to type your work and present it everything in Word, and that way it's easier to see what you are doing. So I believe with this video and with this we have come to the end of Elasticity. So hopefully by next week we'll go to another topic entirely. So have a good day, and thank you for listening.